In Input, we exploit the software-defined networking paradigm in designing a mechanism called the multi-cluster overlay that could realize wide area virtual tenant networks and effectively support dense deployments of mobile virtual machines at the network edge in highly scalable fashion. MCO provides a number of advantages with respect to state-of-the-art SDN mechanisms. To start off, it uses non-overlapping open-flow rules among different overlays without the use of resource-hungry tunneling protocols like GRE or VXLAN, and provides overlay connectivity inside and among data centers at the network edge. It also enables a more abstracted and agile overlay network control through VM aggregation. Moreover, MCO avoids any network-induced performance drawbacks such as packet losses, delays, encapsulation overhead, which typically occur during VM migrations in legacy Layer 2 and Layer 3 networks. All of these are achieved using simple and mandatory OpenFlow filters and actions, as well as Layer 2 addressing criteria. As regards performance, MCO has low computational overhead, and the traffic paths obtained with the mechanism correspond or are close to optimal ones. More importantly, MCO achieves a high level of scalability as it significantly reduces the number of OpenFlow rules in the overlay implementation and the number of rule updates during bulk VM live migrations. Consider, for instance, this telco infrastructure with 10 geographically distributed in-network data centers, and suppose that a VTN owned or managed by a user U is built on top of it, involving a subset of data centers. A VTN delta is associated to an MCO network Q delta, a sort of private overlay specifically designed to provide Layer 2 interconnection among its endpoints. Q delta can have both physical, fixed or mobile, and virtual endpoints, including the user premises physical equipment deployed in the home and or connected through mobile access, as well as the set of VMs hosted within a subset of data centers. As its name implies, the MCO organizes the user's physical or virtual objects into N clusters that are identified with cluster centers C0 through Cn-1, each one mapped to a data center gateway switch in the telco infrastructure. In this example, the MCO network involves 4 cluster centers, C0, C1, C2, and C3, that are mapped to 4 different data centers. There are 13 overlay endpoints. The home termination HU can be understood as the gateway to a fixed home or enterprise network. The set of 2 mobile terminations is denoted by M delta, and the set of 10 virtual machines is denoted by V delta. VMs identified with the cluster center Cn is given by the subset V delta n. For example, V delta 0 contains V1. It is important to note that over time, multiple cluster centers of the same overlay Q delta may be mapped on the same gateway switch ID of the data center D. Consequently, the internal connectivity for Q delta in D will involve all the VMs of all its cluster centers residing in D, denoted by V delta D. The Layer 2 connectivity among overlay endpoints is built based on paths and shortest path trees, where each SDN device such as a physical or virtual OpenFlow switch along a path constitutes a hop. Hence, the terms hop and switch will be used interchangeably hereinafter. In more detail, the shortest path PLR is defined as the optimal sequence of edges and hops from L to R, while the shortest path tree SPTRL is the union of the shortest paths from each leaf in L to the root R. For a given path, 2 edges EI and EO are defined on each of its hops. The direction of the flow either towards the leaf or root is indicated by the indexes I and O respectively. Moreover, on a generic switch H belonging to a shortest path tree, The set script E contains all the edges at H involved in the same shortest path tree. Note that edges are mapped to distinct ports on a switch. In the context of MCO, the overlay connectivity inside the data center D is defined by the shortest path tree SPT ID V delta N, with VMs in V delta N being the leaves and the gateway switch ID being the root. On the other hand, the wide area overlay connectivity is defined by N shortest path trees Q delta Cn, each one rooted at the gateway switches IDN on which their respective cluster centers are mapped, and the gateway switches IDM on which other cluster centers are mapped being the leaves. The MCO forwarding rules are designed based on the exact or wildcard matching of IEEE Ethernet 48-bit MAC addresses and optionally on IEEE 802.1q VLAN tags. Considering that the majority of today's IT virtualization platforms and hypervisors allows the association of customized locally administered MAC addresses to virtual network interfaces such as those of virtual machines, we exploit this feature, setting the universally or locally administered bit to 1 and partition the layer 2 address into 3 fields: the overlay ID, the center ID, and the host ID. The value of the individual or group bit depends on the type of forwarding: 0 for unicast and 1 for broadcast or multicast. The open flow rules are expressed in this way. As regards the rule priority, lower X values indicate higher priorities. Exact and wildcard matches are represented with the operators equivalent and equivalent prefix respectively. The latter is intended for masks hitting the overlay and/or center IDs. The corresponding actions can either be frame forwarding, modification, or group table processing for flooding and more complex forwarding semantics. Note that all rules in the MCO mechanism are meant to be placed in the table 0 of OpenFlow switches. For unicast forwarding inside the data center D, 2 types of exact matching rules are used. A frame is always directed towards the gateway switch ID unless the higher priority rule is matched. This provides direct connectivity between VMs of different cluster centers belonging to the same overlay, such as V2 and V3 in the example. In the wide area network, only one type of rule is used, with wildcard masks hitting the overlay and center IDs. The rule aims at directing unicast traffic from any other cluster center's CM towards CN, and crossing the Q delta CN tree in upstream. Using the Q delta CN tree routed at the destination gateway switch achieves simpler rules, considering that there is only one path and port towards the root. Broadcast and multicast forwarding rules will be almost identical, with the individual or group bit in the MAC addresses set to 1 and some slight differences with the matching field values. Hence, they are treated as 1. Inside the data center D, at a generic hop H belonging to the tree SPT ID V delta D that is not the gateway switch ID, broadcast traffic is forwarded to all edges involved in the same tree. At ID, both data center and wide area connections are considered. Moreover, translation between the universal and overlay broadcast MAC addresses will be performed at the hypervisor switches. In the wide area portion of the MCO network, broadcast traffic generated by a VM bound to the cluster center CN is forwarded to all edges belonging to Q delta CN, crossing the tree in downstream. The MCO can support multiple mobile terminals but only a single home termination. This way, there is no need to translate the MAC addresses of physical hosts in the domestic LAN. In the latter case, the home termination HU is identified with the cluster center CH that is mapped to the switch IDH. We suppose that the switch IH hosting HU is a legacy switch that only hosts home terminations and not VMs. At a generic hop belonging to the path PH that is not the switch IH, the OpenFlow rules use wildcard masks hitting the overlay ID. At IH, an additional filter on the input interface is used for unicast traffic coming from HU. Moreover, translation between universal and overlay broadcast MAC addresses will be performed at IH. For the mobile access case, we suppose the presence of latest generation LTE radio access network architecture in which user terminals can be exposed by the evolved packet core and most likely connected to the overlay at the packet data network gateway level. Consider a mobile termination MU identified with the cluster center CM that is mapped to the switch IDM. The switch IM is supposed to connect user use terminal to the PGW and PM is the port on IM connected to MU. It is worth noting that PM will likely correspond to a virtual port, for instance, the logical termination of a network tunnel as in the figure. Hence, most rules used with VMs are also applicable with mobile terminations, except at IM where translation between the terminal's physical and overlay MAC addresses is necessary. As previously mentioned, one of the main advantages of the MCO is its efficient network support for seamless VM live migrations. Like common approaches for minimizing the service interruption time during such migrations, MCO adopts a two-step procedure. Before initiating the migration, forwarding rules are temporarily configured to duplicate packets destined to the VMs on the move towards both old and new positions. Once the migration is complete, forwarding rules are updated to remove the connectivity to and from the old positions. Moreover, MCO supports this procedure for two types of migration. The first type is the intra-data center single VM migration between two servers. This is a primitive operation mandatory for allowing the maintenance of servers or the dynamic consolidation of data center resources. The second type is the inter-data center bulk migration of all the VMs bound to a cluster center, which we refer to as center migration. This is defined for adapting the location of services in an efficient and scalable way. During a center migration, it is necessary to enable the bidirectional propagation of any packet exchanged among VMs bound to the migrating cluster center CN between the old and new data centers, and to deliver packets from the other cluster centers destined to CN towards both data centers. Once the migration is complete, all forwarding operations to and from the old data center, or at least for what concerns the traffic related to CN, are pruned. The MCO is currently implemented in the Creator module of the OpenVolcano platform. Now we shall see a demo on the OpenVolcano web interface based on INPUT's personal network as a service use case. For this demo, we emulate the Hibernia global topology based on the dataset available at the topology zoo. This topology has 55 nodes, which we distributed into 20 data centers, 17 interconnection switches, and 18 access switches, in such a way that any two data centers are at least 2 hops apart. We also considered 3 data center sizes according to the number of servers available in each data center, which can either be 20, 50, or 100 servers. For instance, this data center has 20 servers. Moreover, the dynamics in the CPU load and memory utilization of each data center are modeled based on the 6-day traffic traces from Dandelion's open data. Now suppose that every user is subscribed to 10 services, each one corresponding to a cluster center with 2 virtual machines. The cluster center C0 maps to the user's virtual home gateway and is fixed. On the other hand, Cluster centers C1 through C9 are mobile and can follow the user as necessary. Particularly, lower cluster center indexes correspond to tighter proximity requirements. Note that VMs can have multiple network ports depending on the number of networks they belong. In this example, 1 out of 2 VMs in cluster centers C1 through C9 are connected to a distinct, service-dependent back-end network in addition to the user's personal network. Several system statistics are available on the OpenVolcano web interface. By hovering on each server, the number of VMs and the percentage of committed vCPU and RAM are shown. The overall data center statistics are also given below, in terms of the percentage of reserved vCPU and RAM, and the number of VMs shown with one slice per server. In addition, the percentage of active servers is also indicated. On the OpenFlow switches, the total number of rules installed are shown, as well as a detailed flow table that includes the group bucket actions on the hypervisor switches. Now, let us add 2 more users in the system. All VMs of the red and yellow users reside in Data Center 4, while those of the green user are in Data Center 25. By looking at the flow tables of their respective gateway switches, we can see rules concerning the red and yellow users with overlay IDs 0457 and 0458 in the former data center, and only those of the green user with overlay ID 0459 in the latter data center. As the red user moves to other access nodes, we can observe center migrations, in which the placements of the involved VMs are updated. When its cluster centers are migrated to Data Center 25, we can see that the flow table at the gateway switch now contains rules concerning the red user with overlay ID 0457. Furthermore, it is interesting to note that center migrations are only initiated if the proximity level is not satisfied otherwise.